is behind it? You need to understand how we get information. Then you are sure that it's something not just invented or some enlightening of some person. So everything what we know about particles has some experimental ground and observational ground. And characteristics are introduced to explain observations. So we have studied radiation energy loss, which is when a particle is propagating in medium and then scatters some charged particles. It acquires acceleration or deceleration and emits photons. So of course it loses the energy. This energy loss is proportional to energy of the particle. And therefore, when particle propagates, loses the energy loss decreases. Opposite situation is with ionization. Which is another mechanism of energy loss of the particle. And the process is that when particle propagates and scatters on atom, it can knock out one of the electrons. So this is our particle X, due to electromagnetic interactions. And one of the electrons go out of atom. So this is the process with exchange of gamma. So the process is like X interacts with electron and go to X and electron prime. The momenta and energies are changed, of course. So this is the process of the second order in the electromagnetic interactions. There are two couplings here, electromagnetic couplings, and therefore cross-sections are proportional to alpha squared. Diagrammatically, the process is like this. This is what we are usually associating to this process. This is Feynman diagram for the scattering. Of course, one needs to take into account that electrons are inside the atoms, but this is relevant when the energies are quite low. So what I will do is the following. As in the case of radiation energy loss, I will write the final formula for this energy loss, and then explain different factors which appear in this formula. So what is this formula which is describing the ionization energy loss? If somebody remembers, knows. What is the name of this formula? It's Bethe-Bloch formula. dE over dx, energy loss on the unit of length, so it's minus sign here, is 4 pi alpha square. So an alpha is coming from our counting, this is second order a weak process, over the mass of the electron. This is essentially reflects the boron radius. I will explain how it appears. But then the most important factor is 1 over b square x. This is velocity of our incoming particle x. So remember, this is important dependence, that ionization energy loss is inversely proportional to the velocity of particle squared, and therefore the slower particle moving, the bigger the ionization energy loss. So this is one of the important dependencies. And then there's a relativistic factor, which is the function of mass of the electron, again velocity of particle and ionization potential. And then we need to multiply by the number of electrons. And this number of electrons is proportional to Z. So if you want to express this in terms of electric charge of nuclei, it's Z, which appears in such a formula.
What's the meaning of I?
Sorry?
What's the meaning of capital I?
So I will explain this one. This is ionization potential. So let me say a bit more. The relativistic factor, F, actually what is really one needs to remember, it increases logarithmically with energy. So there are many stuff which is entering in this factor. I will not, no, probably I will write this explicitly once, but it's not necessary to remember this. So that's 1/2. Sorry that it's not deleted well. The logarithm. What is staying under logarithm is 2 masses of electrons. Then gamma, this is Lorentz factor squared. And again, ionization potential squared. Then minus velocity of particle x squared. And so when particle becomes relativistic, this is essentially velocity of light is 1 in our units. And minus delta gamma over 2. And this is the electric screening, what is called the electric screening. Now, gamma is Lorentz factor. So gamma is E over m. That's 1 over square root of 1 minus velocity of particle squared. And so it's proportional to energy or momentum. And it's under logarithm, which means that this factor is a logarithm of momentum or energy. Right? So that's important to remember. Now, as I said already, is ionization potential. Which depends, of course, on the atom types of the what is Z, what is the atom, and this is essentially energy which is needed to ionize the particle. Now, ME is the electron mass. Again, what is important? This you can, of course, remember immediately. So this is important dependence, and so that's proportional to logarithm of energy with factors. Okay? So this factor again is the same, and essentially it is related for all particles X, and this is essentially related to boron radius. The formula can be derived again on physical ground. Let me give you some sketch of how it can be obtained. dE over dx is equal to the average energy loss in each collision, sigma, cross-section, and number of electrons. So this is general formula which we also use for the case of radiation energy loss. So sigma times Ne is the number of electrons of the unit on the unit. So this is a number of electrons multiplied by sigma. This is the probability of interaction on the unit of length. Right? This can be introduced. And therefore it's clear, so that gives you the number of essentially collisions on the unit of length, and you multiply by average energy loss in each of these collisions. So this average energy loss is close to Rydberg energy. Now, cross-section is given by pi, then Bohr radius squared multiplied by opacity. So again, on classical level, what you have, you can represent your scatter as some area, which is semi-transparent in general for your particle. The radius is given by the size of the atom, which is given by Bohr radius. So that is Bohr radius, let me remind you, is 1 over alpha m(E), and this is the origin of mass in denominator there. And then opacity factor is given by alpha squared over V squared. Now, why opacity is inversely proportional to velocity? And the point is very simple. The probability of ionization is proportional to time squared. And this is the time during which particle is flying through the atom. Because if it flies slowly, then the more chance that it will interact with electron and knock it out. And so this time is inversely proportional to velocity, and therefore the probability is inversely proportional to velocity squared. The square is when we go from classical to quantum level. This is usual what appears if you want to have a connection. So if you collect all these factors, and by the way, Rydberg coupling also depends on alpha, it's energy, sorry, this energy is alpha squared mass of the electron over 2. So here is squared. And then if you collect all the factors, you will exactly get this expression. So physical meaning is again very simple. This is number of collisions, number of interactions per centimeter. We multiply this by energy loss in each of these collisions. This energy is of the order of Rydberg energy, which is alpha squared here. Now, another alpha squared in the denominator appears here in the Bohr radius, but it is square and therefore it cancels. And what is left is alpha squared, which gives you transparency. Now, so this is Bohr radius, and this is the opacity or transparency of your atom.
And the factor F? How could you derive it?
Which factor is?
F.
Oh, so that's complicated. And you need to, that's relativistic. So I'm saying that.
Okay, you only went for the physical for the other part.
Yeah, so for this part.
And the other, you have to go to quantum field theory.
Yeah, you need to go to relativistic. So this is classical stuff, very simple, and then you need, this is more involved, of course, this part, which gives you a logarithm of energy. At least I haven't tried. Maybe one can even produce this. I haven't tried. So I did this for these prefactors. Actually, for all energies, this is more important stuff, and we will discuss this.
So actually, we know that the cross section is kind of like the target area that the target gives to a particular incoming particle. So if you have an atom which is not a hydrogen atom, you have a heavy atom, then shouldn't you write pi into radius of that atom square? Because Bohr radius means that you're considering hydrogen atom.
Well, you are right, but everything is counted here eventually. Number of electrons. So essentially, if particle has the energy bigger than the binding energy of atom, then what you count this number of density of electrons already. So that gives you an idea. I put here proportionality. Yes, of course, atom is bigger for heavy atoms. So you need to put some factors if you want really to have exact expression.
So you are saying that that sigma is proportional to pi into RP square.
It's of the order of Bohr radius square. typical size of the atom.
What's the Rydberg energy?
Well, this is essentially energy of ionization from the lowest, deepest state. Of hydrogen, but again, so if you have bigger atoms, then. But this is of the order of magnitude. At least you see how these different factors appear in this image. Okay, so let me.
So for low energy is the domination in the F factor, what would be?
What do you mean low energies?
Let's say that I'm not sure. For gamma close to 1, let's say.
So for
the velocity of x, there is low.
yeah, let me show you the plot. Maybe that will give answer
Okay.
to your question. So let me show you dE over dx as function of velocity, if you want, or a momentum of particle p. So typical dependence is like this, then some minimum, and then it will be a logarithmic growth with momentum of the particle. So here is this 1 over velocity squared, which is p squared, and this is mass squared, right? So it's inversely proportional of p squared in this range. So that minimum is approximately at momentum, which is 3 masses of the particle x, and then we have logarithmic growth here. So this energy's logarithmic growth becomes dominating. Now your question coming back. So here is like 1 over v. The smaller velocity, the bigger. So it's kind of
And is the electric screening, what is the depend? It depends on gamma, okay. But
yeah.
does it become relevant in some part of the plot?
This is a good question. I think it becomes relevant at this proof. Let me not to cheat. I don't know exactly. So that's screening because you have electrons and scattering on different electrons start to influence each other. So that to some extent reflects this dependence.
So where?
So naively I would say it should be somewhere here. But no, I think because you have also this relativistic effect, this is relativistic factor, I think it should be here by kind of definition. So that enters this relativistic factor. So it should be at higher energies.
Okay.
You will have some exercise, but again, the most important region is this one. I didn't see where the energy loss is big. Now remember how the radiation energy loss increases linearly, and it actually becomes important at some high energies, usually in this part. And the energy at which radiation energy loss and ionization energy loss become equal is called critical energy. So this is called critical momentum. Since we put here P, so this is critical momentum. Critical energy. So this is non-relativistic part, right? So this is non-relativistic. This is relativistic part. Now let me give you some examples of this energy loss and critical energy. And I will give these examples for proton and for electron. And let me first consider a heavy material like lead. In lead for electron, critical energy is 7 MeVs. So you see it's 3 of electron mass, which is 1.5 MeVs, and the critical energy is somewhere here, 7 MeVs. Radiation length for electron in lead is 0.56 centimeters. So which means that if you have energy or momentum of electron 300 MeVs, then dE over dx, which is energy over Lr, as we introduced this, that will be equal 535 MeVs over centimeter. So it's even bigger than the energy, which means that the energy will be decreased by 2.7 factor at a distance which is smaller than 1 centimeter, or something like 0.5 centimeter, 0.50 something centimeter, to reduce the energy by a factor of 3 or so.
Are radiation lengths dependent on the temperature
Temperature.
of the material in which they are?
Remember, it doesn't depend on energy. So what we have derived this for, it doesn't depend. I don't think that it depends, at least in the first order. So it's just constant. So remember, I introduced this. Now for proton, again, let's take P equal 300 MeVs. It's non-relativistic, right? It's in this rising range. So we can find immediately that critical energy is approximately given by critical energy of electron multiplied by mass squared ratio of these particles, and you will get something like 3 × 10⁴ GeVs. So the critical energy for proton is much bigger than the mass of the proton. So mostly the proton will lose the energy on ionization. So for heavy particles, this is dominant mechanism of energy loss. And dE over dx will be approximately 80 MeVs centimeter. So which means that if you take proton and electron with the same momentum 300 MeVs, then electron will lose the energy much faster than the proton. Okay? And it will lose the energy on ionization. So this is typical stuff. When particle is heavy, it loses less energy than lightest particles. Let me make a summary of properties of these two mechanisms of energy loss. So probably, let me see if Probably I will give you another example when we have not heavy medium, like here the lead, but light medium. And in the light medium, like carbon, we have the following. The radiation length for electron is 18.8 centimeters. It's bigger because remember, this radiation energy loss is proportional to Z squared. And critical energy is 100 MeVs. So one can compute that dE over dx for 300 MeVs electron will be something like 16 MeVs over centimeter, which is much smaller, first of all, the energy, and it's much smaller than we had for heavy elements. This is just because of this strong dependence like Z squared. In the case of proton, again the main energy loss is ionization, although here is still radiation. dE over dx is 40 MeVs over centimeter. They are comparable. So if you have materials with kind of light materials, then the energy loss of electron and proton become comparable.
So here the proton is losing energy more rapidly than the electron.
Yes.
So it means that it is not always true that the proton will lose energy less rapidly.
Yes, it's not always, yeah. I would say typically, when I said that heavy particles lose energy. Well, proton here you see it's comparable, right? In this one.
For example, if we suppose that instead of proton we have helium nucleus, which doubles the charge.
Mm-hmm.
So how will it affect the the rate of energy loss?
Oh, you need simply because you know what is the scaling. So if you want to have radiation energy loss, then radiation energy loss is proportional to Z squared. But still, since it's heavy particle, then ionization dominates. Now, ionization, then you need to compute what is velocity of this particle. You need to tell me what is the energy or momentum. And remember, the ionization energy loss is inversely proportional to velocity squared.
Because I'm asking this because when they teach radioactivity, they say that alpha particles have a shorter range than the beta particles. So is it true that it is dependent on the material in which we are investigating?
It also depends on material, yeah?
Yeah. They don't tell this. I don't know why, but they just only say that alpha particles have a shorter range than beta particles. So probably
well, you can rescale actually easily because all the characteristics, the most important, are here. So what you need to have a density of electrons. Let us think about ionization. So the most important parameters are this 1 over V squared, and then number of electrons, which actually is proportional to Z, the density of electrons. So material enters here, now density. And here you have non-relativistic particle that you need to take into account mass. So the velocity is momentum over the mass of the particle. And if you take helium, then it will be 4 times bigger.
probably they're talking about air when they say that they have a shorter range than beta particles.
Yeah, so if you take helium, then velocity for the same energy will be smaller than for proton. Right? So it's V, then it will be like dE over dx will be proportional to the mass square. Right? Because it's inversely proportional to velocity, then it will be inversely proportional to mass. So let me compare radiation and ionization. So what I will compare dE over dx. And in the case of radiation, we have dependence P over mx squared, where this is x is our particle which loses the energy. In the case of ionization, the dependence is mx squared over p squared, and I will put here me in denominator to have the same dimension for these two things. You see, it's inverse. It's proportional to p here and inversely proportional to p squared here. It's inversely proportional to mx here, and it's proportional to mx squared here. It's different. So which means that with decrease of p, so here dE over dx decreases, and here it inversely increases, which is important for observations. And we will discuss the things that increases. So, which means that if particle is moving and if ionization dominates, then what happens is that it loses the energy, moves slower, and the energy loss increases more and more. So, we will see the tracks of the particles, and in the case of, let me put here radiation and here is ionization, the tracks will have the following behavior. In the case of ionization, the energy loss will increase, and therefore the track becomes bolder and bolder. So the particle moves in this direction. In the case of radiation, it will be opposite. So it loses more energy in the beginning if radiation dominates, but then the energy loss becomes smaller and smaller, and so the track will be like this. Okay, so this is the distance. This is the distance, and the width of the track is proportional to energy loss. Okay. So then, important feature, which I have already mentioned, that here it's 1 over mx squared dependence, and here is proportional to mx squared. Now, here we have dependence as z squared. Here we have dependence as z. Z gives you, density of the electrons is proportional to z. As I mentioned already, in heavy elements medium, we have dE over dx for electron, which is much bigger than dE over dx for proton. And in intermediate range of Z elements like oxygen, carbon, these two energy losses are approximately the same, comparable. Questions?
To know if radiation or ionization is dominating, we have to look at the rate at which energy is in loss. Is that the idea?
Sorry, say again?
Okay. So to know if it's more probable to have radiation or ionization, we have to look at what is the energy that is lost. Is that the idea?
Well, experimentally what you see the track, you see where particle comes from, and if you see the track which becomes narrower and narrower,
Yep.
then this is radiation energy
okay, I
loss.
see.
So this is typical for ionization energy loss. So then you can guess what's going on, what is the dominating mechanism.
How can we, the obvious way to differentiate between the ionization loss and the radiation loss is that we can detect radiations and ionization, and that from that data we can know how much is the radiation loss and how much is the ionization loss.
Well, so you see, even in the case of radiation, so what's going on? Elementary process is emission of gamma, but then this gamma still ionized the medium.
Yeah, that's what I'm asking. So
Yeah.
how will you differentiate between the electrons which are purely from ionization?
No, but originally the energy deposit is from your particle. And therefore, if you have radiation that in the beginning you have more photons emitted, right? And therefore the integral mostly, so you have even ionization which is bigger, which is secondary now in the process, which photons eventually ionize.
I'm asking that suppose that there's a track of a particle and it loses energy by both processes. Yeah, it is losing energy, but both processes near the critical frequency, near the critical
Yeah.
energy. And then how will we differentiate that?
Well, it's
these
then
energies by
then it is then one needs to analyze and to see more carefully what's going on.
what do we have to say?
Well, we need to have, you see, we usually apply magnetic field, but one after another I will explain different discoveries. So then you can understand what is the momentum of the particle.
Momentum of the particle which is emitted by ionization?
So again, you can see the track. Suppose you don't know what is ionization or radiation, but you see the track and you can see the curvature of your track in the magnetic field. If you see this curvature, that gives you immediately the momentum of your particle, independently on x. And then actually, usually what people are doing, they are analyzing data. Say, okay, suppose this is a radiation energy loss, and to see what are the consequences once you know the momentum. Maybe it's not, you will see some discrepancy somewhere. But then you assume that this is ionization or radiation. So that's kind of the way we analyze data. We assume one or another mechanism and then see what we are getting.
But is there any way to differentiate between, suppose that there's a particle which is losing by ionization procedure. Okay, then it means that from the track there will be electrons coming out of the track, and we can detect those electrons. Is that the way, or is there any?
Well, you do not see this. So if you do not see this electron individually, usually you do not see.
No, detect them, do not see them.
And detect you see it. We will discuss just start immediately to discuss after this how we see the tracks. So usually it's again you have ionization, which you do not see immediately ionization. Then we see some kind of appearance of droplets or discharges. It's more complicated. You do not see these electrons from ionization immediately. So they produce secondary macroscopic effects. And this is what we see really. So there is again elementary process, then usually ionization, and then ionization produces macroscopic effects which we can see.
So sometimes it's easier looking at certain histogram because they have certain shapes that you can identify. And you just characterize your experiment and you see that there is a shape here that is ionization, another shape that is radiation. Of course, there is something in between, but if you have
well, this is related to essentially to this property.
Yeah.
What you are saying. Okay, we will discuss specific discoveries, and then I hope I will explain what's going on. Okay, now we will discuss yet another process, which is Cherenkov radiation. So who knows what is Cherenkov radiation? I don't know. Oh, you know, good. So how important Cherenkov radiation is for energy loss? When it is important?
I think when the particle energy is greater or near the speed of light in that particular medium.
No, I mean in terms of energy loss. So we discussed these two mechanisms as mechanisms of energy loss. Then there's this Cherenkov radiation. How big is the energy loss due to Cherenkov radiation in comparison with these two mechanisms? So that is my question.
Constant, around 2 meters. It's a constant decrease.
No, whatever. Okay. So
Compared to those, it's very small. Compared
yeah.
to this
So that's important way to explore the properties of the particles. However, for energy loss, it's not very important. It's much smaller than to other energy losses.
Because if it was very important, then it would have been a primary source of attraction, but the primary source of energy losses are ionization and radiation, because those are used.
Yeah. Well, you are saying this axiom, no? But you need to. Okay, come on. So okay, let me explain what is this Cherenkov radiation. Well, Cherenkov radiation has been discovered by Cherenkov, actually by Vavilov and Cherenkov. And Cherenkov got a Nobel Prize, fortunately, because Vavilov was dying by that time. So Cherenkov and Vavilov, actually Cherenkov was a student of Vavilov, and so they observed some luminescence in medium and observed some non-trivial blue shining when particles are moving, when this material is exposed to radiation, cosmic ray radiation, for instance. So for a while it was not clear what is the source of this radiation. So eventually Tam created a theory for this radiation. Now what is the mechanism? So we are saying that the particle is moving and emits Cherenkov light, which is not quite correct. So what emits light is medium. So what happens is the following. Particle moves in dielectric medium, which means this is not conductor, otherwise this radiation would not exist. And particle polarizes medium around itself. And so what emits light is medium when you have first polarization of molecules around the trajectory of particle, and then depolarization. So then, because when you do this polarization, particle is excited, and then particle moves, and then in the medium, so there is a de-excitation, again emission of light. So this is medium, polarized medium, which emits this light. Now schematically I can show you in this way, particle, and suppose this is negative particle, and then what happens is that you have plus, minus, have molecules and atoms which are polarized, plus, minus. Now, polarization is strong when it is close to the particle, then when you go further, polarization becomes weaker, so I need to put here, and then it disappears. So we have something like that. Here is strong polarization, then it becomes weaker, and then it essentially disappears. So what happens, you have polarization. First you have emission of light when you polarize particle, and then depolarization also you can emit a light. So that's what's going on. So one can treat actually all the system of polarized molecules as a big dipole. So here particle is negative, and mostly you have here minus, and here is plus dominated. Sorry, here is plus, and this is minus if particle is negative. And so you have kind of dipole. Particle is moving, create this dipole, and then the excitation produces the light. So what we are saying is coherent growth and decay of these dipoles. That create the Cherenkov light. Now, not only this is important. What is important that Cherenkov light, or what we call Cherenkov light, is emitted when particle is moving with velocity which is bigger than the phase velocity of light in medium. In this case, coherent front is produced. Coherent front of radiation. So, which means that what is emitted here, so you have emission of the light, and if the condition of this fast moving particle is satisfied, then the light which is emitted forms the front, coherent front, which means that in all other regions these photons or light, it adds some up incoherently, which means with different phases, and therefore is to some extent decreasing the amplitude. And only in some certain ranges or regions in the fronts where these waves are summing up coherently, and therefore here you have enhancement of radiation along the certain fronts.
And this angle depends on the velocity of the particle?
Yes, so we will derive this.
It is just like the sonic boom.
It's like it's like a shock wave.
Yeah.
So at lower velocities, radiation is also emitted by the decoherence cancels effect.
So when you have low velocities, then the front is not even formed. Just we can see this geometric picture, which I will show you. Okay.
For the circle, if you consider the circle, then they are never catching up with the circle. Which are
Right. So different circle from the emission from different points, they will be inside. So you cannot have, which means that eventually we will give. How we do consideration when we are doing quantum mechanics? We first solve the wave problem, right, and then give particle interpretation. So this means that most probably you will see the photons along these propagating fronts. Of course, there is some light here, but it's incoherent, and therefore the number of photons which are outside of these fronts is much smaller. So mostly they are in these fronts. Now let me first start with phase velocity, and I will develop a wave picture first. So phase velocity. And in medium, we describe propagating light by plane waves. Which includes refractive index, K, N, and X. And here, N is refractive index. So the phase itself is F is energy T minus K and X. And so if we have wave, then phase velocity gives us the velocity with which, for instance, maximum in your wave is moving. Now, what is expression for velocity? So equal velocity, equation for equal velocity is given by K and X is constant. And from here we obtain that X equals E T over K N minus this constant over K N. And phase velocity is given by dx over dt, which is given by E k over n, and we deal here with the light, and therefore E over k she is just 1 over n. It's 1. Oh, yeah, refractive index in our units. So which means that if you have medium with n bigger than 1, then velocity will be smaller than velocity of light. Let me put here index h. So the phase is moving with velocity smaller than velocity of light. So what is interesting that for water, n is 1.33, so it's not a joke, it's a substantial deviation from 1, and therefore phase velocity in water substantially 30% smaller than velocity of light. Now let us derive a equation for this front and to see how the front, coherent front, is formed. So let us consider particle which is produced in some space-time point. Let me put this x0 at t0. It propagates and it is absorbed at some another point, x fine, at tf. So, for instance, neutrino produces electron at some point, and then electron is absorbed by some nuclear atom. Stops. Okay? So we will neglect for time being energy loss of particle when it propagates. So then we will include the energy loss. So let us find what is the distance from trajectory of particle of the light in the moment of time t of p, which is in between these two times. So where the light is, where the front of the light is at this time. Again, so let me show this picture back. So what's going on is, so this is, we are looking everything in the moment of time TF. So particle propagates and then emits the light at the distance xp. This is x equals 0. And then in the moment of time TF, light propagates and form the front. This way, something like this. And what I want to find where this light was in this point. So what is this x gamma? So again, I'm looking for this distance x gamma to which the front is propagating when it is emitted at the point xp, by the time tp of the particle. So here we have our particle. It emits at this point and then light propagates and it is somewhere in the moment of time tf. So time is given by xp over velocity of particle. So this is the moment of time when the light is emitted. So therefore the light propagates the time tf minus tp. So this is time of propagation of the light. And therefore xf is given by this time multiplied by velocity of light. Let me put gamma. So I'm again talking about this front of equal phase. So following how the phase propagates.
V of gamma is the velocity of light.
No. So this is phase velocity. Okay, this is the same what we introduced as phase velocity.
Then shouldn't it be x gamma? In the formula, should it be x gamma?
So this is the distance which a given front is reaching in the moment of p. So I'm following. Actually, there's of course certain time, and it's not just one line, but a given phase. So this is the sphere of a given phase.
But that given this sphere is at the time tf.
It's given at the time tf. So whole story is the following. I'm looking on the portrait of kind of how the radiation is looking like in the moment of time tf. By that time, what happened is the following. Particle propagates certain time and then emits in a given point xp light, and then light propagates, and the time of light propagation is this, tf minus tp, the rest.
That's what I'm saying, that it should be x gamma in the left hand side of the last formula. Instead of
Here?
No, there.
Oh yeah, sure, sorry. It should be gamma, sorry, yeah, of course. This is our it's gamma. Yeah, sorry. Clear? So, this is essentially the equation for the front. So it gives us x gamma as the function of xp. So this I have considered for a given point, but then I will take another point like xp prime, and what will happen is, again I will get some front of this type, then another point I will get something like this, then like this, and I will get these spheres which correspond to emission of the light from a different points x. So here it will be x prime prime, here it will be xp prime prime prime, and all they will be obeying this property. This means that I can write this curve which touches all these spheres. So the biggest one is when particle emits starting from the beginning, so I will get something like that. And this equation precisely gives me this line, the line of the front. So again, when I change xp, and this is the point in which a particle emits light, I will get the equation for x, and essentially I'm getting for a given p these distances which the phase propagate, and it will be so they will be at along this line. So this is the function x gamma or xp.
In a little mathematical terms, we can say that these circles is a family of curves, and this is the envelope. Of
Yeah, exactly. So that's if you want this envelope, but this is maximum. This is the radius. If you want a radius of all these circles, and what happens is that this radius is simply a linear function of x, and that proves that they have the same line, which they are kind of embedded in the same code. So you see, when particle is here and just start to emit here, then the radius is 0, right? The biggest radius when particle was emitting here. So again, what I'm repeating, particle is moving, and it emits a light in each point of the trajectory. Then I just pick up one of these points and have found this equation, which is actually applied to any xp along this trajectory. And I'm neglecting energy loss along this trajectory, assuming that this radiation doesn't take much energy, at least. So have this image. Questions?
Why is the energy loss so small, supposedly?
You see, the energy loss onto radiation is on this Cherenkov radiation is small, much smaller. Right. But of course, electron loses the energy on ionization, and one needs to take into account this, and that actually changes. It changes velocity of particle. Particle is moving slower, and therefore it changes
the angle of
it changes the angle. Yeah. So we will come to this.
Why is the Cherenkov radiation usually blue?
Well, this is because it has 1 over lambda dependence. 1 over lambda dependence, and then so when you have some kind of maximal energy of the photon which can be emitted, and so that gives you this brown.
Can Cherenkov radiation be ultraviolet?
Sorry?
Can Cherenkov radiation be ultraviolet?
Well, it has a little bit even in ultraviolet, so it's blue, but close to ultraviolet region. Again, so give me 10 minutes and we will arrive at this 5 minutes. So that's on agenda. So what we have, and when the energy loss is small, suppose the trajectory is quite short. So that you produce particle, and it has very small tracks, 10 centimeters, and then absorbed. Absorbed. So it collides or lose the energy on some hard collision. So that's the end of the story.
I see.
So, suppose that the particle is at xp and there is a light going from xp. So the wavelength of that particular light is the same as the wavelength of the Cherenkov radiation, or is it different?
What we are talking about Cherenkov radiation, which means again the radiation not a given particle, but it's property of the medium,
Yeah, or the medium.
right?
So are these two wavelengths the same?
So we assume that this is the same, yeah.
So can we work out the wavelength of this radiation from the properties of the material that okay,
Of
how
course,
that type
yeah,
is
of course, yeah. So that has been done.
That has
Sure, yeah.
So is there any medium which emits Cherenkov radiation which is not blue, but visible but not blue?
That's a good question. I don't know. Usually, what people are using water or some scintillators, and in these cases, it's blue. But it should depend on medium. I agree.
So are they using water because it is polarized?
It's because this deviation from one is very big. One.
Why don't they use glass? Why don't they use glass? Glass has almost 2.
Well, it also produces, of course, but for some other reasons, we want to have some water. For instance, in many detectors, we use water or because we don't want only to do this, but for some other things. So usually scintillator, which is again oxygen, hydrogen, or carbon, or water. So that's, but of course it should depend on the properties of medium.
So
Water is cheaper. Water is
And
cheaper.
water is cheaper is another reason.
So, is this particular value of refractive index of water is the only reason because of which we use water? And
Well, again, the second reason that's cheaper.
So the polarization of water is not.
Well, another reason, sorry, is because it's a proton rich. If you want to study a scattering of something on protons, then water is. It has oxygen, but it has almost 3 protons.
Okay.
And Cherenkov radiation is also used with neutrino, right?
Yes, to detect again electrons. Imagine.
With like neutrinos in
Yeah.
some.
Not immediately neutrinos. So what's going on? You have, for instance, neutrinos, which produce secondary electrons.
Yeah.
And this is what happens in a superconductor, for instance. Then these electrons produce Cherenkov radiation.
Okay, and in that superconductor, they use also water?
They use also,
Water?
yeah, water.
They have a lot of water.
Precisely. Yeah. Yeah. So again, you're asking questions because I'm going to talk about this,
Okay.
including the superconductor stuff. But again, for time being, what is important that in this way we have derived this equation for the front. Yeah.
Can you, for example, have Cherenkov radiation from vacuum fluctuation, polarized vacuum? Is that possible, or
Ha.
because you have
Yeah. So what you want to say that we have this kind of operators like this is what is called vacuum polarization operator, right? Plus and minus. Well, I think this is what for Cherenkov what is important that you have really. I don't know. That's kind of what we call polarization operator, right? So what we call if you have vacuum expectation value of scalar field. So what we have, what else? Because this you cannot consider as a medium, right? So that's it's a virtual particles you produce these virtual particles. So my answer is no, I don't think so, because you need to really to have dielectric medium to have these real molecules are filled in by some stuff. And
even if you apply a strong electromagnetic field on the vacuum?
I don't think that you can.
I think that because this phenomena requires that the 2 points from where the light is emitting should be it should be like that the light the light wavelengths should interact. So in the vacuum, I think that the 2 points from where the radiation is coming should be space-like separated.
Well, you can still say okay. So you can think about the vacuum as some state made of particles, usual particles, right? In principle, right? So you have the lowest state, which is these packed particles, but when particle is moving, you see, you need to have some system like molecules with plus and minus, which you can polarize. A given molecule, I don't know what be corresponding to polarization of, so if your medium is composed, but this is not what really realized in nature, of course. I'm just speculating. So my answer is for in realistic situation, no, you cannot do this. You need to have this medium. So don't confuse polarization of medium and these polarization operators in elementary processes.
And there is one more thing, that suppose that you have a dipole and it is not, the dipole is not changing with time, then it is not going to do any radiation.
Well, you can say also, suppose again, if your medium is filled in by, so lowest state of but this is usually not even charged particles, usually it's a scalar particle, it's neutral, and but you still may introduce some charges. Again, I'm speculating, this is not, so the answer is, in the situation which I know, the answer is no. Good. So, looking at this picture, what you have is the following. Since particle is absorbed here, nothing is emitted when it is propagating here. So, the beginning is somewhere here when particles start to emit in the production point. So, what you will have front of finite size, right? So, there is no front here, there is no front here. And this is in the moment of TF, when particle reached this absorption point. So what will happen when T is bigger than TF? Nothing already is emitted, particle disappeared. And so what you will have propagation of this front of the finite size. So you will have this. But of course it has this cylindric symmetry, right? So you have also front here. And you have this conus, right? So it's conus in the moment of time at TF, but then it starts to propagate, and you will have the picture like, so this is when it is produced, and then you have the propagation of the front, and I'm writing across this two-dimensional projection, and we have the fronts here. So this is what is called Cherenkov cone. So this cone is formed within which you have propagation of the line. Now what is direction? So what is this T? Cherenkov, along which this front propagates. So again we can use this picture, and this is the same angle as here, T Cherenkov. And then in the moment of time TF, so the length of this side was V gamma times TF. So this is the length of this. And now the length of this is V particle times TF. And this gives for me cosine of the angle. So again, using this geometric picture, I can find what is cosine of this angle, which is ratio of this side over this. Okay? So this corresponds to propagation of the light when it is emitted in the initial moment t0, and so we find what is the length of this side, and this will be V gamma times TF. The length of this corresponds to particle propagating, and then it starts to emit in the final moment of t. So the length of this is velocity of particle multiplied by TF. So then this cancel, and I will have V gamma over V particle. And if particle has velocity of light, then it will be, if particle has velocity, which I will call, what we have here, velocity of gamma is c multiplied by, over over the refraction index. And here we are usually using beta, as beta is velocity of particle over c. So bottom line is that the angle, let me write this, cosine theta Cherenkov is given by c is 1 as 1 over n times beta. And beta is velocity of particle in the unit of velocity of light in vacuum. So this is expression for cosine of Cherenkov angle. Now, if n if beta decreases, and so this is becoming closer to 1, then what happens is that the angle decreases. So the angle is decreasing. Let me show you this, what's going on. This is answer to your question, what's going on if you have energy loss of particle. So if the track is long enough, then what you will have is that because of energy loss, beta decreases, and this n times beta approaches 1, and therefore cosine approaches to 1, and theta ch approaches 0. So what you will have is the following. So if in initial moment you have the cone of this type, then after some time, because of energy loss, it will have smaller angle, then even smaller, then close to just to the line, and then it disappears. So when you have n times b equals 1, when b is decreasing enough, then the cone radiation disappears. Okay? Now let me comment on the case when you have velocity of particles smaller than velocity of light, phase velocity of light. Then instead of such a picture, you would have the following, again particle. So then this is the sphere of equal phase in the initial moment. Then when particle is here, it produces a sphere of this type. Since particle is moving slower and light moves faster, when it is here, it produces something like that. And you never form the front because these spheres emitted, they are inside one, inside another. So this is the situation when the velocity of particle is smaller than the phase velocity of light, gamma. So only when you have light which propagates faster, so you see this distance, which is radius, the given radius, is smaller than this distance. It's smaller than this, so it will never go out of the previously emitted sphere, and therefore one sphere turns out to be inside another sphere, and the front is not formed. So only if you have the situation when, say, second sphere is somewhere here, the next one is here, and this happens when particle moves faster than the velocity of light. And so in that case, you will have formation of the front.
If they are equal? If they are equal?
Well, so if they're equal, then you have such a situation that cosine is 1 and the angle is 0.
Okay.
Now the spectrum. What is the spectrum of radiation? So this is actually, Tom has derived. dN, number of photons, or dx of d lambda. So I can switch now from the amplitude of waves to the number density of photons. So you need to square amplitude, then it will give you the probability of to observe the particle. So it's given to 2 pi electric charge 1 minus, and here it will be beta square n square and 1 over lambda gamma squared. So dependence on the material only here, so you ask, so it's an n. And then the end of the spectrum is, so it starts from, let me write it. So what you have here, no, choke. We have somewhere. So what happens is that you have this dn over d lambda, and here is lambda, the wavelengths of Cherenkov radiation, and you have something like that. This is 1 over lambda squared dependence.
The variable x means the distance that the particle travels.
So this is energy loss. I have written for energy loss, and here just written because I think it's the n over the lambda essentially. So, but this factorizes because then I need to write here the number density. Saying, think about this. Maybe I should delete this. The n over the lambda. This is the spectrum. It's a lambda square. I'm not sure about the units, but that's important dependence that lambda is sitting here. Now, what happens is that actually refraction index also depends on lambda gamma. And this cut of the spectrum again corresponds to the situation when n lambda, this function of lambda, is 1 over beta, when that becomes 0. Even in water, so this n changes with lambda, and therefore this is what gives the cut here. And so cut depends on this lambda. Your question was what about the materials? So the properties of the materials enter here in dependence of refractive index as a function of lambda. So the spectrum cuts if you have this equality.
So there is a cutoff wavelength. It means that there is a cutoff wavelength for the material.
And also cutoff depends on beta. So that corresponds to such a situation. Finally, what I want to say a bit about Cherenkov rings. Suppose I have some surface with sensitive elements which can detect your light. You have here trajectory of your particle which emit Cherenkov light, And then what you will see as a projection, you will see the ring inside which you will have signals. Like that. I should show it better. Okay. So usually people are putting some photomultipliers on the walls of the detector, and then the particle emits this Cherenkov cone. Projection of this cone on the plane will be the Cherenkov ring. So what is detected as the signal along this Cherenkov ring? And in fact, studying these Cherenkov rings, one can get various information. So, for instance, the width of this ring will reflect the length of trajectory. Right? So if you have long trajectory, then you will have more bold ring. So you can measure direction. So if your particle is moving perpendicularly to the surface, then you will have an ideal ring. If you have some inclination, then you will have ellipses here, not rings. So you can measure direction. You can also measure the energy of the particle. Looking at the intensity of the radiation. And not only this, you can find what it to guess what is the nature of the particle. So, for instance, you can easily distinguish between electron and more heavy particle like muon. So, this is realized in detectors like Kamiokande, super Kamiokande. Now people are discussing hyper Kamiokande. It's one of the working detectors is super Kamiokande. And this is water Cherenkov detector, literally. So that's a huge cylinder, detector is in Japan, which is filled in by 50 kiloton of water. You can guess what is the size of this huge cylinder. And the walls of this filled in by water, and there are photomultipliers on the walls of this detector. So what they see in this installation, you see these precisely Cherenkov rings on the walls of the detector. Now, how to distinguish electron from muon? Muon is particle which is quite similar to electron, but 200 times heavier. Electron is light, and what it's doing, so it has kind of multiple scattering in the medium. So it's not just flying directly, but its trajectory changes slightly when it's moving. It's like this, multiple scattering. This is electron. And therefore the cone produced in different parts of this trajectory will slightly shift. So what one will see in this case, diffuse, not sharp borders of the ring, but diffused because of change of the cone of the emitted by electron. In contrast, muon, which is a heavier particle, its multiple scattering is smaller, so the trajectory is more straight, and for muons you see sharp borders of this cone. So you see how rich information can be obtained from these simple things. So, and actually identification or distinguishing of muon from electron is very high. So I think like in 5% of the cases you can confuse electron from muon. And then what people are usually doing, they calibrate detector, which means they have, for instance, small linear accelerators putting inside, which produce the beam of electrons, and you know that these are electrons. And therefore, then they see what is the signal, so they can really kind of calibrate that. This kind of the rings with these diffusion borders correspond to electron. Questions?
Do you get any signal from this multiple scattering?
Sorry?
Do you get any signal from the multiple scattering of electron?
What do you mean signal?
Like when it's
So
bouncing?
they will see independently of Cherenkov,
Yeah.
or what? So in this, at least in this detector, so what they see diffuse some rings without sharp borders.
Yeah, that's because of the changing direction of the Cherenkov curve, but
Yeah.
in very particular for this event, is there any photon released in each bouncing?
Oh, so usually this is very small signal. This is so-called multiple scattering because it's scattering with a relatively small angle, and but multiple, many scatterings on the trajectory. So nothing drastic is happening, and of course it's difficult to detect any signal. So, questions? Finished. So this is the sign that I should finish now.
No, a few minutes ago.
Okay.
What
Questions?
What about CTA?
About
CTA, the Cherenkov telecon array.
yeah, this is Cherenkov for cosmic rays, cosmic gamma rays detector. So huge detector, and the Cherenkov light from the air. So that's what.
It was a very high limit in energy for particles.
And these are very high energy particles, so they produce, yeah. That's water, but indeed you can use air as a medium, which produces this.
It's not hard to differentiate the signal from this event from the rest of the world. Have like an open.
In CTA or what? Or
In
here?
CTA.
So here, so look, here they see these rings. You can confuse with number of rings because sometimes you produce not just single particle, but you say produce two particles, and then you have a messy picture, and you have overlap of few rings. So now in the case of CTA, I'm not sure that I'm the right person to ask. I'm not on this. But again, so they have sensitivity to Cherenkov light. So most probably what you are detecting, so dominant signal will be from Cherenkov light. That they for sure know. Now, how precisely they measure these rings? This is, I don't think that they really measure the rings. So they have these installations and they see the signal. Because what you produce showers. Usually it's not just single particle, but many particles propagating. And each of these particles produces Cherenkov light. And so you do not see this kind of the rings. So you see this blue type of the radiation in the detectors.
How often you can be looking for photon decay with this?
Oh, this photon decay, again, so you can measure in this way any charged particles, right? So one of the modes, it depends on the mode, is for instance pi 0 and a positron, and then pi 0 decays into two gammas. And in fact, since gammas are also converted, so gammas are very quickly, they can actually scatter on electrons, but also they can be converted into a plus and minus. And then these particles will produce a Cherenkov light. Essentially everything is reduced to, in this case, to electrons. So you have this ring produced by this A plus, and two other rings which are eventually produced by the gammas, which are converted to charged particles. So it's a three-ring event, and you can expect something like this from this pi decay, from this proton decay. course, there are some other modes which are more difficult to detect, like, for instance, proton can decay into neutrino and K meson. Then some radiation can be, but K is not so very energetic, K decay, and then you can see the Cherenkov light produced by the products of K. Kelvin is another hazard which we will discuss later. Okay, then see you tomorrow.
Recording.